Greetings, this is Dr. Gross, and welcome to another installment of Easy SPSS, an easy introductory guide into running statistical analyses on IBM's SPSS statistical analysis software. And so the first thing I'll do is open up my SPSS package on my desktop. And when I see the splash screen appear, I'm just going to close it. And we have previously saved a data set, so I can open that by going to File, Open, Data. I can do it that method, or I can just go to the Open File folder, and here I saved in Documents my intro video SPSS data. So I'm going to open that up. And now I have my data set ready and waiting. And today's tutorial is an introduction to simple linear regression, which is one type of statistical method that's used to examine the relationship between two continuous variables. An independent variable, which is used to make predictions and is thus called the predictor variable, and a dependent variable, which we're trying to predict or explain. Thus, we can refer to this dependent variable as the outcome variable. The purpose of simple linear regression is to apply a line of best fit, otherwise known as a regression line, through the data that shows the relationship between the two variables. This line represents the best estimate of the dependent variable based on the values of the independent variable. For example, we might want to examine whether age, an independent variable, predictor variable, can predict or explain the height, our outcome or dependent variable, in our sample. And you might say to yourself, well, age is a great predictor of height for certain age groups. For children, for instance, we could predict height between a 2-year-old and a 9-year-old and say that age is a good indicator of height in that instance. We won't be using children's ages in our sample, so we'll see if our sample can get to a level of statistical significance. When would you use simple linear regression? Anytime you're trying to make a prediction, to predict one value of a variable based on another variable, or if you're simply trying to show that a relationship exists, understanding the direction of that relationship and the strength of the relationship. So a positive or inverse relationship, and then the strength of that relationship, a -1 to a +1 correlation. A -1 and +1 indicating the strong, very strong relationship, where a value of 0 would indicate no relationship, and values approaching 0 would indicate very weak relationships. So a bit of a refresher for SPSS. You have two main views, data view and variable view. Data view is showing you the actual data and each case or participant in a spreadsheet-like format, where each row is going to be your individual case or participant, and each column represents a variable. So here we are in data view. I'm toggling over that tab. And in data view, I can see that each row represents a participant or a case in our sample, and each column represents a variable. I'll switch to variable view, and here you define the attributes of each variable. For example, the name, the type, and the measure. And accuracy in variable view setup is paramount to SPSS being able to recognize data types and perform these statistical analyses correctly. So always ensure that your data is set up correctly in variable view. So let's switch from data view to variable view. And in variable view, I can see the 4 variables that we have identified: ID, gender, height, and weight. The type for all of them is numeric. We applied labels for ID, such as identification number, gender, male or female, height in inches, weight in pounds. We were just getting a little bit more specific with the information on our labels. For the value column, the only data we coded was gender, and we coded 1 for male and 2 for female. And to do that, I would click on the ellipses right here, those 3 dots, and it brings up my value labels box, dialog box. And here we can add labels or values. So we added a 1 value and told SPSS that 1 means male, and the 2 code is representative of females. The measure is very important. For continuous data, we set the measure to scale. And for categorical data, we would set the measure to nominal. So perhaps a good thing that we did the brief refresher, because we're going to add a new variable. We're going to add the variable age. So first thing we're going to do is switch to variable view. And in the first empty row, you're going to type age in the name column. So I am in variable view. And in the first empty row in the name column, I'm going to type in age. Next, I'm going to set the type to numeric and the measure to scale, since age is a continuous variable. And additionally, we can add a label like age in years. So we're going to set the type to numeric, measure to scale, and we're going to add a label. So we're going to set the type to numeric, which is the default. We don't have to do anything there. We're going to set the measure to scale. And then for the label, we can say age in years. So now we have identified a new variable in the data set, age, and we have defined its attributes. Next, we're going to enter the actual data for age in data view. So we're going to switch back to data view, and in the age column, I want you to enter the following ages for each participant. So let's go back here first, and from variable view, I'm going to switch over to data view. I can see the new variable has been added, age in years, type numeric, the measure is scale. And I am going to manually enter in this data in data view. So go ahead and pause your video and enter the ages for each participant, 1 through 12, as shown on screen. After you enter it, make sure to save your data set to just make sure those changes are kept in case we want to play around with this data in future videos. So go ahead and pause, and I'm going to move over to data view, and I'm going to input this data right now. Great. So my age data has been entered for participant 1 through 12. Oops. Better save it. So I can save by clicking save, or I could go to file and then save. So let's run the test. We're going to navigate to the regression menu by going to Analyze, Regression, Linear. So let's do that now. We're going to go up here to Analyze, Regression, Linear. And you will see the linear regression dialog box open. From here, we want to define our dependent and independent variables. So we're going to move height to the dependent box, our outcome variable, and we're going to move age, the predictor variable, to the independent box. So let's move height to dependent and age to independent. So let's do height to dependent and age to independent. Next thing we'll do is run the test. So click OK to generate the regression output. All right. So we now have some output that we need to analyze. And you will see three tables that come out of this regression output: the model summary table, the ANOVA table, and then the coefficients table. And so if I go to our output, I can see the model summary, the ANOVA table, and the coefficients table. And I'm just going to kind of move that over to the side a little bit. Let's see if we can keep this on screen. See if we can, let's just do this. So in the model summary table, the R is the Pearson product moment correlation coefficient. And the correlation coefficient between age and height will indicate the strength and the direction of the relationship. R squared represents the proportion of variance in height, which is explained by age. For example, in our model, R squared is 0.053. That means that age explains only, if we multiply by 100, 5.3% of the variance in height. Right, values closer to 1 would indicate a much stronger model. In the ANOVA table, we have the F statistic, in this case, 0.446. And if significant, the F statistic suggests that the model provides a better fit than a model with no predictors. So if we look at the significance of the model, the p-value is 0.523. Now, a p-value of less than 0.05 would indicate a statistically significant model. In our example, significance, or the p-value, is 0.523, which is far above 0.05, suggesting that age does not significantly predict height in our sample. Right, now, we know that it could very well be a great predictor of height in children, but we did not include children's ages in our sample data, and it probably would not have correlated with the heights that we have input. So I would expect not a significant model in this case. So the coefficients table, right here where it says constant is the intercept. And this is the expected value of height when age is 0. Although it might not have like a real world meaning, it helps in understanding the regression line. The slope, or B, for age, it represents the change in height for each 1 unit increase in age. For instance, a slope of negative 0.1. A slope of negative 0.1 would mean that height decreases by 0.1 inches for each additional year of age. However, our model is not significant with a p-value far above 0.05. And so in this case, interpreting the slope is not really necessary. So again, in this example, R square is 0.053, meaning that age only explains 5.3% of the variance in height. It's a very low value. It's a very weak relationship between age and height in our sample. The F value of 0.446 and with a significance value of 0.523 shows a p-value that's far greater than 0.05. So the model is not statistically significant. And what that means is we don't have sufficient evidence to conclude that age significantly predicts height in this sample. Again, the coefficients table, the slope or the B value shows the direction and the magnitude of the relationship. Again, with a p-value greater than 0.05, the slope itself is not statistically significant. And that indicates that any observed change in height could just be due to random chance. And so to summarize the results of this regression model that we just ran, in this example, age does not significantly predict height. R square suggests that age only explains a very small proportion in the variance, only 5.3%. The high p-value in the ANOVA table indicates that the model does not reach a level of statistical significance, meaning that age in our sample does not reliably predict height. And we mentioned that, the purpose of simple linear regression is to apply a line of best fit or a regression line. And so I wanted to end by showing you what that actually looks like. So we're first going to create a scatter plot with a regression line. So we're going to go to graphs, and that's kind of hard to see. It keeps getting in the way. We're going to go to graphs, legacy dialog, and then to scatter dot. I'm going to select a simple scatter, and I'm going to click define. So in the simple scatter plot dialog box that opens up, we're going to move height to the y-axis and age to the x-axis. And we're going to click OK to create our scatter plot. And so let me upsize this. Here's our scatter plot. And if I were trying to apply a line of best fit, which kind of is in the middle of all these dots, so to speak, I suppose it would, roughly look like that. I'm not exactly sure. The data is kind of spread out, very dispersed. And so what I'm going to do next is I'm going to double click on that scatter plot in the output viewer, and it's going to open up chart editor. And within chart editor, I'm going to go to elements. So let's do this as we're talking about it. So I'm going to double click on my scatter plot, and it's going to open up the chart editor. And in chart editor, I'm going to go to elements and select fit line at total. And this plots our regression line for us in y equals mx plus b form. There's your slope. There's your x-intercept. There's the y-intercept. And there is the y-coordinate. Right? And this is giving you proposed or predicted height values based on age. Right? So for a 28-year-old, we would have a predicted height of 65 inches, roughly. Again, this model is not significant, so our regression line is not a good predictor of height as determined by age in our sample. This is, however, how you would determine and plot your line of best fit or your regression line in your simple linear regression model. So again, the regression line is it's representing the predicted relationship. And it's created by minimizing the distance between the observed data points and the predicted points on the line. And how would you interpret it? Each point on the regression line represents the predicted height for a given age based on the model. And again, I could go here to the regression line and say every point on this line is a prediction. So for age 28, the predicted height would be roughly 65 inches. Again, our model is not significant, and so that would not be appropriate to do. The slope and the intercept, the slope indicates the change in height for each 1 year increase in age. And then the intercept is the predicted height when age is 0. So in our example, the regression line shows the predicted trend of height as age increases, but just on the specific data that we used. So in this lesson, you've learned how to set up data, add a new variable, run a simple linear regression, interpret the results, and plot a regression line in SPSS. Next steps would be probably to explore additional predictors, or preferably work with larger samples to better understand relationships in the data. Thank you for tuning in, and stay tuned for our next episode, where we will cover additional statistical analyses in SPSS. Thanks for watching.